Today, we're diving into a seriously ambitious new blueprint in advanced mathematics known as the FUCG program. And look, this isn't just some new chapter in a textbook. It's a huge effort to build a kind of universal language, one that connects the geometry of really complex shapes with the fundamental rules of physics. So let's break down what that actually means.
So here's how we're going to tackle this. First, we'll get into the big picture, these mathematical bridges the program is trying to build. Then, we'll see why it was so important to move past just a single dimension. After that, we'll unpack the new toolkit it created, check out what it's already accomplished, and finally, look ahead to the new frontiers it's opening up for future discoveries.
All right, so with a project this massive, you've got to ask the first question. What is it really trying to do? What's the core mission here?
At its absolute core, this project is all about building bridges. The author, Mohammed bin Amar Trady, is aiming to connect three incredibly powerful but traditionally separate areas of science. First, you got Kählerian geometry. You can think of that as the math used to describe the complex, multidimensional shapes that might just be the very fabric of our universe. Second, there's spinorial analysis. That's basically the language of quantum physics, what describes the behavior of fundamental particles. And third, you have mixed Hodge structures, which are kind of like a super deep algebraic filing system for sorting these unbelievably complex shapes. For a long time, these fields have all spoken different languages. The FUCG program is designed to be the universal translator.
Now, this work is actually volume 2 in a series, which, begs the question, why the jump? Why was it so critical to move beyond the one-dimensional world of the first book?
Well, this leap into higher dimensions is where things get really exciting. See, in one dimension, you're pretty much just dealing with lines and loops, simple stuff. But our universe, well, it's not a simple loop. The second you add more dimensions, the geometric possibilities just explode. All of a sudden, the math has to describe these incredibly intricate shapes, like the Kählerian manifolds that some physicists think are the fundamental building blocks of reality and string theory. The old tools just weren't going to cut it, which is why a whole new framework was needed.
So, to explore these higher dimensional worlds, a brand new toolkit was needed. It's got three core parts that work together in a sequence. First, you define the universe of shapes you're studying. Second, you build a tool to analyze them. And third, you create a system to actually read the results.
First things first, you have to define your field of play. And that's this category called FUCG. It essentially lays out the rules of the game. It says, okay, we're only looking at this particular family of complex shapes, specifically what are called compact Kähler manifolds that have an extra geometric feature known as a spin-Kähler structure. This step is all about focusing the investigation on the shapes that really matter.
So once you have your universe, you need a tool to explore it, right? That tool is the spinorial complex K.X. Honestly, you can think of it as a highly sophisticated scanner. It takes one of those geometric objects from the FUCG universe and probes it with a sequence of really precise mathematical operations, all to extract its most fundamental properties.
And here's the payoff. After that spinorial complex scans an object, it produces a totally unique output, the invariant FUG of X. Think of this as the object's unique mathematical fingerprint. And because this fingerprint is a core, unchangeable property, it allows mathematicians to reliably identify a shape and, crucially, to compare it to other shapes. Okay, so we've got a new universe to explore, a new scanner to probe it, and a way to generate these unique fingerprints. So the big question is, what has this new toolkit actually allowed us to build and understand so far?
The single biggest achievement is the creation of a powerful comparison engine. It gives mathematicians a formal, rigorous system for comparing any two shapes in this universe. And it works in two directions. You can take one shape and project its properties onto another, and you can also trace those properties back again. It's this two-way street that lets them create a precise map showing how all these different, complex geometries relate to one another, building a solid foundation for analysis. Now, as impressive as all these results are, this work isn't really presented as a final destination. In fact, its most exciting part might be that it's laying down the serious groundwork for an entire open research program. The journey is really just getting started.
So, where does the research go from here? Well, the author lays out a really clear roadmap of the major open problems that are going to define this field for years to come. And these are not minor questions, not at all. Each one is a potential breakthrough. For example, lifting the entire structure into an even more powerful framework would give it even deeper algebraic properties. Proving this metric anomaly conjecture would reveal how those fingerprints actually change as the geometry of space itself is bent and warped. and of course, extending the theory to new kinds of shapes and connecting it to other frontier areas of math and physics, well, that promises a whole new wave of discovery.
Ultimately, what this work by Mohammed bin Ammar Charaidi provides is a rigorous new language and a robust set of tools for exploration. It's like having a detailed map of a newly discovered world, complete with coordinates, landmarks, and clearly marked frontiers. The foundation has absolutely been laid. The only question that remains is, what new mathematical bridges will be built next?